2.7, and it is called implicit differentiation. Up to this point, when we've taken the derivative of stuff, it has always been in the form y is equal to 2x plus 3. Solve for y, right? Every single one of them. And so we didn't have to talk about these. We just take the regular derivative and we don't worry about it. But there are some times when we have equations, like maybe for circles. So it said x squared plus y squared is equal to 4. That's a circle that's got a radius of 2 that's centered at 0, 0, right? Sometimes I have to do some stuff with some circles, and I need to be able to take the derivative of those circles. But if it's not solved for y, I can't take the derivative the way that we've been doing. So what we do is instead of trying to solve this for y, which gets kind of ugly because we have the plus and negative square root of stuff, and then that starts turning into just a nightmare as you try to take the derivative of it. It's much easier if we just do the implicit differentiation. The only thing new that you need to know is that when you take the derivative of y, you have to actually write the derivative of y with respect to x. So you take the derivative of the x pieces and the constants the same way you've always done it. But when you take the derivative of y, the derivative of y squared is 2y dy dx, because it's the chain rule. That's why we do this after the chain rule. I'm going to take the exponent down in front, right? Then I'm going to write the thing in the variable or whatever's there that's being raised to a power. I'm going to reduce the power by 1, and then I take the derivative of the thing that was raised to a power. For the x, I never have to worry about that because the derivative of x squared is 2x dx dx. The derivative of x with respect to x. Well, anything divided by itself is just 1, right? So this is just 1. That's why I've never worried with it before. This is not 1. This is the derivative of y with respect to x. This is actually the notation for the derivative. So what happens when I do implicit differentiation is that as my last step after I take the derivative, then anything that's over here with the dy dx has to be brought to the other side. So in this case, I would be dividing by 2y on both sides of my equation. Okay? So in other words, what you do with implicit differentiation is you do exactly the same way you've been doing it. You take the derivative of all the pieces individually. Just know that anytime you take the derivative of anything with a y in it, you've got a dy dx for the chain rule, because you took the derivative of that piece. And then you've got to solve for dy dx. Yep. Makes it so much easier if you do that. It was a good idea to go ahead and move the, solve it for the y first. It's not always as easy to do, but solve it for y, have everything that's got a y in it on the left-hand side of the equation, everything without a y on the right-hand side, then it makes it fewer steps after you take the derivative and it starts looking more complicated. Okay? So let's look at one of those for an example. And they actually use the example close to the one I had on there. So we'll just go ahead and use that for an example. We got x squared plus y squared is equal to 4. They use x squared plus y squared is equal to 1, but it's going to give us the same idea. Okay? So first of all, part A, they want us to find the derivative, find dy dx. And then part B, it wants us to find the slope of the circle. I can't really use their x equals 1/2. Yeah, but they actually gave the whole ordered pair in the book because they used the unit circle, and they got the point, that point off of the unit circle. You remember we studied. So we're just going to go ahead and just leave it here because we'll find it. Okay? All right, so the derivative, dy dx. So we've got x squared plus y squared is equal to 4. So the derivative of x squared is what? Oh, before we get started, it's easier to move it. So we get y squared is equal to 4 minus x squared. Now the derivative of y squared we already said was 2y dy dx. What's the derivative of 4? 0. And the derivative of negative x squared is minus 2x to the first. Right? And then, like I say, your last step, this is the new step, is you want to divide both sides by whatever is multiplied by dy dx. So my final answer is that dy dx is equal to a negative. The 2's cancel out, right? X over y. So my derivative is going to look different nowadays because why? There's going to be more than one letter. It won't just have x's in it, right? It's going to have y's in it too. So if I want the slope of the circle, right, at a certain point, then how do I find the slope before? I took the x value and put it in the derivative, right? That's how we find the slope, is we take the x value and put it in the derivative. Well, my derivative is this. So I can take that 1/2 and put it in, but what's true about my derivative? I need the y now. Okay, so that's the new thing. So before you can go on to actually find the slope, you actually have to take this x value and plug it back into the original equation to find the y to go with it. Okay, so we have 1/2 squared plus y squared is equal to 4, right? 1/2 squared is 1/4. So we've got to subtract 1/4 from both sides. So y squared is equal to, is that 16 over 4? So it'd be 15 over 4. Just so it's in a fraction form. Square root. So y is equal to a positive and negative square root of 15 over 2. Right? When I take the square root to solve something, I have to have the positive and the negative value. 15 is not a perfect square, so I'm just going to leave it in there. But the square root of 4 is 2. So I can take the square root of the top and the square root of the bottom separately. So I actually have two different slopes, right? Because, you know, that kind of makes sense. I got a circle. When x is 1/2, I've got a point up here and a point down there. So I've got this point where I've got negative 1/2 divided by the square root of 15 over 2. And I also have the derivative where I've got a negative 1/2 over a negative square root of 15 over 2. And then if you, this is a complex fraction, so you invert and multiply. That's a negative 1/2 times 2 over the square root of 15. 2's cancel out. And I get a negative square root of 15 over 15, right, because I rationalized it. It was actually 1 over the square root of 15, but I never leave it like that. Y'all remember that from trig? So it becomes a square root, negative square root of 15 over 15. And then I do the same thing for this one. Got a negative 1/2 times a negative 2 over the square root of 15. 2's cancel out. I get a positive 1 over the square root of 15, which is the square root of 15 over 15. Multiply the top and the bottom by the square root of 15. You can't leave a denominator with a square root in it. So any questions about that? Okay. Quick check 2 is on page 186. Gives us another one to do. We're supposed to find dy dx for x minus y squared is equal to 3. So we got another one where it's not easy to solve for y. So the easiest way to do this is using implicit differentiation. So to simplify our world, we can go ahead and subtract the x from both sides. And then if you want to get rid of the negative sign, you can. That's up to you. You want to multiply through by -1, so I've got a positive y squared. So I got y squared is equal to -3 plus x. So I multiply the entire equation through by -1. And now I take the derivative. So I've got 2y dy dx is equal to 0 plus 1. And so dy dx is 1 over 2y. So for implicit differentiation, if they ask you to find the slope of the line or the curve at any particular point, what are you going to need? Just the x value? You're going to have the x and the y. Okay, so you're always going to have to, if they just give you x, you're always going to have to plug it back into the original equation so that you have your whole ordered pair, because it is going to take both coordinates most of the time. In this case, as you see, the x is what disappeared, and I still have a y. Okay? All right. Let's